Hello. Can everyone hear me? A big yes. Okay, so gather from the comments there was a big chemistry exam last night. How was that? I shouldn't laugh at another department. Uh, I didn't think Proctor Track was going to work. I heard about that. Well, I'm glad that was amusing. So anyway, I saw that. I'm still trying to get the angle on this right. Hi everyone. Um, so anyway, I saw that somebody was wondering what today's poem would be. I thought we'd start with something slightly different. So if I can get the sharing working. Let's see. Worked a little faster. We're going to start, first of all, with 10 seconds of a babbling brook. So give that just a second to work. So that's part of today's humanizing effort. By the way, were you able to hear the audio on that babbling brook? Oh no, okay, so it doesn't pick that up. Oh well, it actually was making sound. So anyway, I recorded that with my phone on, hold on just a minute, one of my walks through the park. So let me tell you where that was. So instead of a poem today, we're going to talk about the pole farm. I think I mentioned this the other day. So there's an old technology before there were ubiquitous wireless phones, and before there was I saw that comment. That's nice. Before there were undersea cables, carrying terabits of information constantly. The original technology that was used to make phone calls overseas was something called shortwave radio, and like anything else, just like computers, they were enormous and took up entire rooms and had roughly the power of a four-function calculator. Now, on a chip the size of your finger, you can have all the computing power you want. So, if you look at the picture on the left, these are enormous antennas, roughly as tall as the Statue of Liberty, that existed in the 1920s, and they stretch on for about a mile down a field. And they stretch on for about a mile down a field, and they could carry exactly 4 phone calls. In fact, not even 4 phone calls, but rather 4 half phone calls. So many of you know AT&T is based in New Jersey, and AT&T was, of course, the company that was engaged in this enterprise. They're headquartered in roughly Red Bank or Middletown. So they put their receiver in Middletown, but to avoid interference, they had to put the transmitter 45 miles away in order to avoid the radio interference. So they bought this huge tract of land and set up enormous antennas that together could carry just the transmission side, in other words, the voice going from here to England, of 4 phone calls at a time. And this thing was called the London Array. Eventually, they switched to the technology. That's what you see on the left. Eventually, they switched to the technology that you see on the right, which was called rhombic antennas that were much smaller than this. Basically, if you look at it closely, what you'd have 4 poles in roughly a diamond shape, and the point of the diamond was pointed at another city, and they could put many more of these. They tore down the big antennas you see on the left and created these rhombic antennas pointed at many, many cities. Um, this park, of course, nobody uses this technology anymore. It was torn down in 1975, but they created Mercer County, New Jersey, created a park that's basically dedicated to this particular history of the dawn of the electronics and telecommunications age, and it happens to be about a mile from my house, so it's kind of a fun place to walk. That's where the Babbling Brook was, in the park that's now called the Pole Farm. I photographed down here. You can see this is the last pole standing. They just left one pole standing, and according to the plaque next to it, this was part of a group of 4 poles carrying the rhombic antenna that was aimed at Tel Aviv. So anyway, that's today's history lesson. Somebody said they actually know where this is, so. All right, so anyway, let me flip the laptop over, and we will start with today's actual math. All right. Okay, so we begin today with, let me see, actually easier for me if I turn the webcam off, because you really need to see the content, not just me. So sorry about that. You'll have to remember what I look like. Okay. So we start today with the mean value theorem. The mean value theorem is, as I mentioned, there are a number of theorems in calculus that end with the phrase value theorem, and this is one of the ones we're going to learn. The mean value theorem says, you can read the statement, it says that assume that f is continuous on the closed interval AB and differentiable on the open interval AB. In other words, the interior of that interval, and there exists at least one value C in the interval such that this equation is true. So what's the picture of this, really? So if you imagine, I don't like that color for this. So if you imagine that I have some function like this, that's B, and that's A. I have these 2 points. This is going to be A, f of A, because we can always write that for any point on the curve of a function. They all look like, x comma f of x. So if I draw the secant line connecting these 2 points, the question is, what is the slope of that secant line? The slope of the secant line is going to be y2 minus y1 over x2 minus x1. So I subtract the y points and the x points and divide them. That's going to be f of b minus f of a. Those are the y's over b minus a. And that, of course, is this expression that you see right here. So what it's saying is that somewhere in this interval, somewhere in between a and b, there has to be some point c such that the tangent line has the same slope as this secant. In other words, that it's parallel. In other words, that the tangent line is parallel to the secant. And what the theorem asserts is that this number c that you see right here, where clearly f prime of c is equal to the slope, that value, f of b minus f of a over b minus a, where that value exists. So this is what the mean value theorem asserts, is that as long as the function is differentiable on the interval, somewhere in the interior of the interval, there has to be a point where the tangent line has the same slope as the secant line that connects the 2 endpoints. So this is actually a little bit, it's not just a little bit, it's actually sort of a generalization of Rolle's theorem that we learned the other day. So if you think about what Rolle's theorem is really saying, is just draw a picture of Rolle's theorem. that's A and that's B, then here the secant line that connects these 2 points together is going to be horizontal because FA and FB are the same. And what it asserts is that somewhere in the interval, there's a horizontal tangent C. So Rolle's theorem is really a special case of the mean value theorem. The reason we do them in this order is because historically, Rolle's theorem was proved first, and then you use the property of continuity and a little algebra to prove the mean value theorem from Rolle's theorem. I'm not going to spend time proving the mean value theorem from Rolle's theorem just because we have other things to do. But basically, these are 2 related theorems. The mean value theorem is a generalization of Rolle's theorem. You mostly have to know Rolle's theorem because it often comes up by name in questions that you'll see. But really, you can just think of Rolle's theorem as the special case where FA and FB are equal to each other, because in that case, of course, if this is the point A, F of A, and this is the point B, F of B, then in the Rolle's theorem case, you have F of B minus F of A over B minus A, but that just equals 0 over B minus A, which equals 0. And that's, of course, what Rolle's theorem is asserting, is that there's some point in the interval where the slope of the tangent is equal to 0. Okay, so any questions about that? Yes. Full slide, I think.
Oh, it was an inside job, bro. It had to be. Oh, fuck.
Oh, wait a second.
Inside job.
Sorry, I forgot to mute everybody. Okay. All right, so let's see. What sort of problem can we solve with the mean value theorem? Okay, so you often see these problems. I'm not crazy about this language, but I'm just using the book's language where they say verify the mean value theorem for a particular function. What they really mean is verify that a particular situation that they give you satisfies the hypotheses of the mean value theorem. Recall that every theorem is really of the form if H, hypothesis, then conclusion. So go back to what the mean value theorem says. It really has sort of a compound hypothesis. It says, it's really like saying if f is continuous on closed AB and differentiable on open AB. So those are the hypotheses of the theorem, and then we can draw the conclusion. So what we have to do is verify that the hypotheses are satisfied. So, first of all, let's verify. Well, actually, that's all we're really going to do. Verify hypotheses satisfied. So we know that if f of x equals the square root of x, then f of x is continuous on closed interval 1, 9. How do we know that? Because we know that all powers of x are continuous wherever they're defined. And we also know that f prime of x is equal to, this, by the way, equals x to the 1/2. That's going to equal 1/2 x to the negative 1/2, or 1 over 2 root x, which is, the point is that 1 over 2 root x exists for all x that are greater than 0. Obviously, we can't put a negative number in under a square root sign. We can't put a 0 in the denominator, but we can put in any numbers that are greater than 0. So that means that since 1 over 2 root x is defined for all x in 1, 9, therefore f is differentiable on 1, 9. Okay, so we have the hypotheses are satisfied, and we can say, therefore, there is at least one C. There could be more, by the way. It doesn't have to be just one. In the interval 1, 9, such that f prime of C is equal to f of 9 minus f of 1 over 9 minus 1. We can draw that conclusion. So the next part of the problem is actually find that value. So first of all, let's actually evaluate this expression. F of 9 minus f of 1 over 9 minus 1 is equal to the square root of 9 minus the square root of 1 over 9 minus 1. That's going to be 3 minus 1 over 9 minus 1, which is 2 over 8, or 1/4. So the assertion is that there must be, in the interval 1, 9, there must be some tangent line that has a slope of 1/4. So now what we do is we just solve the equation f prime of c equals 1/4. Nothing magic about 1/4. It's just that in this particular problem that we determined that happens to be the slope of the secant line, so that's the one we're looking for. So it gives us 1 over 2 root c equals 1/4. Let's come up here. Gives us 2 root c equals 4. I'm just using the cross products to do that. Root c equals 2, so c equals 4. And if I draw this, here's the square root function, like that. So let's say that that's 1, and that's 9. So here's the slope of the secant line. And the assertion is that there's some point where there's a parallel tangent line, like that. And the claim is that that is the number 4, or C. Okay. So anyway, that's what the mean value theorem says. It seems like a little bit of an oddball topic in this place, but when we get to the very end of the course, we're actually going to use the mean value theorem in a remarkable way to show the connection between the slope of a function and its area. So, any questions about this problem? Sure, last chance. Okay. All right, then I'm going to turn ahead. Actually, wait a minute. Forgot to copy one of those slides. Okay. All right, so we go on to the definition of increasing and decreasing. This is a review from pre-calc, actually. I remember we covered this at the very beginning of class. So we say that f is increasing on the interval AB if this condition is true. So condition that if x1 is less than x2, then f of x1 is less than f of x2. And we have the opposite definition for decreasing functions. So I've drawn on the left what this means. What it means is that I can pick any 2 points, x1 and x2, in the interval a and b. And as long as x1 is to the left of x2, f of x1 is going to be lower on the y-axis than x2. For a decreasing function, it means that I can pick any pair of points, x1 and x2, and as long as x1 is to the left of x2, then f of x1 is going to be higher on the y-axis than x2. So you can see, just from the shape of these functions, we sort of imagine that an increasing function is one that rises as we move to the right, and a decreasing function is one that, as we move to the right, in both cases, the decreasing function, moves down while the increasing function moves up. That's sort of our understanding, at least sort of intuitive understanding of what those terms mean. We also introduce here the term monotone or monotonic, which refers to the quality of being either increasing or decreasing. So a function that is entirely increasing on an interval or entirely decreasing on the interval can be characterized as monotone or monotonic. I guess I prefer as with many things in this book, particularly in this chapter, we use slightly different terms. I've always learned the term monotone. For some reason, the authors of this book prefer the term monotonic. It makes no difference. You'll probably hear me use either, but I guess I usually revert to my preferred term, monotone. So let's see. So this, of course, this slide has absolutely nothing to do with calculus. This is just an algebraic definition, but the next slide will show the connection to calculus. So we say that we have this theorem called the monotone function theorem. Again, once again, in a slight divergence with terminology, our book calls it the sign of the derivative theorem. Its more common name is the monotone function theorem. And what it says is that we can detect whether a function is increasing or decreasing on an interval by looking at the sign of its derivative, by looking at whether the function's derivative is positive or negative on that interval. So if the derivative of the function is greater than 0 on the interval, we say then the function is increasing. If it's less than 0, then it's decreasing. Again, we draw a picture and it makes a little bit more sense when we do. So here, if I have some interval a, b, and the function on that interval, I just want to make this a little bit more pronounced. Try once more. There we go. So if you look at the various tangent line slopes that you find along this function, just draw little line segments to indicate those. What you can see is that although the slopes are different, all of them clearly appear to be positive. So this is an increasing function. On AB has a positive tangent slope. And I can do the same thing with a decreasing function. Really hard to draw a function that's purely decreasing like that, but there we go, A, B. So here, if you look at the tangent slopes, you can see that they're all negative. So this is decreasing. AB. Now notice we're not actually changing the definition of increasing and decreasing. I'm not saying that now the definition that now the definition of a decreasing function is one where the derivative is negative. That's why this is called a theorem. The definition of decreasing and increasing is still what it is. It's still this algebraic definition, but we now have a theorem of calculus that says that we can, that rather than have to perform this whole algebraic computation of figuring out whether f of x1 is less than f of x2 or not, we can just find the derivative and determine based on the derivative whether the function would meet the formal definition of increasing and decreasing. There's something you have to be a little bit careful of, though. It's not something we make a huge deal of, but there is a slight difference between the monotone function theorem and the definition of increasing and decreasing. And you can see it if I just draw this function here. So here I've got A and B. I'll put in this number C, where you notice there is actually a horizontal slope at that point. So I'm going to ask, where is f increasing? And there are three choices: C, CB, C, AC. Okay. I wish I had the poll feature up, but let's just do this by chat. So what do you think the answer is? Use capital letters A, B, or C, and select all that apply. I'm sort of interested in why so many people are selecting B without selecting A. What is it about A that makes you think the function is not increasing on AC? Oh, no wonder, because I didn't. Yeah. Sorry, I did this yesterday too. I put the wrong letters in. That's what I meant to say. Okay. There we go. The answer is actually A, B, and C. So this example is just intended to demonstrate the slight difference between the derivative understanding of increasing and the formal understanding of increasing. The reason is that if I were to pick this, we know that it's C, f prime of C is equal to 0, because that's the way I've drawn it. But it's still the case that if I were to call this, let's say, x2, and this is, let's say, x1, it's still the case f of x1 and f of x2 obey that same order. And it's still the case also that if I were to put in, let's say, x3, so now here's f of x, not cubed, but f of x3, then it's still the case that x2 is less than x3 and f of x2 is less than f of x3. So there's no reason we have to exclude that one point in the middle just because it happens to have a derivative of 0. So you have to be a little bit careful about the slight difference between the monotone function theorem that gives us this really nice derivative-based test for whether a function is increasing and its formal definition. So what I'll tell you is that if a function if its derivative just zeroes out for one point, and then it goes, notice the derivative here is still positive, and then the derivative here is also positive. All it does is it just touches down on 0 and then goes right back up from positive to positive. Then that doesn't really prevent the interval from being from being increasing. Okay. Any questions about that definition? Okay. Okay, so typical question you might ask in with regard to increasing and decreasing is something like this, like find the intervals on which a particular function is monotone. Let's just do a fairly simple one. So we know that function is monotone on an interval if it's either increasing or decreasing on the interval. So what we want to do is find all the intervals where the function is increasing and all the intervals where the function is decreasing. So we can do this through the monotone function theorem. We're just going to find derivative f. So we know that this is a fairly simple derivative to find. This is 2x minus 2. So 2, now we want to find where f prime is greater than 0 and where f prime is less than 0. So we simply solve the inequalities. So that's where f prime is greater than 0 and x is greater than 1. And similarly, we can solve 2x is less than 0. Sorry, 2x minus 2 is less than 0. 2x is less than 2. X is less than 1. So this is where we're going to see increasing and decreasing. So answer the question. Answer is f is increasing on the interval 1 infinity and decreasing on negative infinity 1. And question, of course, is where is f monotone? So just to be clear on what the definition is and how you apply it, we'd say f is monotone on both negative infinity comma 1 and on 1 infinity. Okay. All right, so anyone have any questions about this? Oh, good question. So when can a function not be monotone? Okay, let me attempt to answer that. Let's do something like this. Say, heck, I might as well use this as an example of the sine function, like that. Okay, so I'm just going to put in the points where clearly the function changes from increasing to decreasing. So this is f of x equals sine x. Here's pi over 2. That's pi. Here's 3 pi over 2. That's 2 pi. So we would say about this is f is monotone on the following intervals. 0, pi over 2, pi over 2 to 3 pi over 2, and 3 pi over 2 to 2 pi. And of course, I've only drawn like a little piece of the sine function. So I'm only considering the part of the sine function that goes from 0 to 2 pi, even though we know that it goes on otherwise. So here what you can see is that there we go. Here we have clearly a positive derivative. There's a negative derivative there. there's still a negative derivative there and a positive derivative there. You can see that slope lines are negative, positive in some regions and negative in others. So the point is the function is monotone on these intervals because it's either increasing or decreasing on the intervals that I've listed. In other words, here, this is an increasing interval, this is a decreasing interval, and this is an increasing interval. What we would say is that f is not monotone on the interval 0 to 2 pi, because on that interval it changes from increasing to decreasing and then back to increasing. So it's not so much that functions are either monotone or not, but a question of where are they monotone. So here we can say that the f is monotone on the given intervals, but it's not monotone on this larger interval. Does that answer the question? Okay, good. So in general, that's kind of a theme of calculus. We've seen that from the beginning, that we didn't say that a function either is continuous or not. We just said that it's continuous in some places and not others. So it's often an issue of whether where a particular function has a property, not whether it does or not. I mean, functions that have a particular property everywhere are very, very nice, but that's often we're interested in where a particular property exists. Okay, so there we go. Okay, so now we return to the subject of critical points and what this increasing and decreasing has to do with that. So we get to what's called the first derivative test. And some of you had asked the other day, if I have a critical point, how do I know if it's a min or a max? And that's actually a very good question, because if I simply give you this point and I tell you that this is a critical point of some function, can you say is it a min or a max or not? Well, you can't, because all it is a point. I can't say whether it's the lowest thing around, the highest thing around, or neither. So what you'd need to know is some context. Obviously, if the function looked like this, we'd be able to say that it's a maximum. On the other hand, if the function looked like this, we'd be able to say that it's a minimum. So the first derivative test allows us to figure out whether a critical number is a min or a max, as a local min or a local max, based on what the value of the derivative is near on either side of the point. So the first derivative test says, let C be a critical point of f, then if f prime changes from positive to negative, in other words, as we go to the right, if f prime is changing from positive to negative, then f of C is a local max, and if f prime changes from negative to positive, then f prime of C is a local min. Like all these theorems, the statement is often sort of scarier than the actual understanding. So I put in this sort of general understanding is, if you were climbing a mountain, the peak is the point where, when you're climbing to get up, you climb to get up to that point and then you descend to leave. So if I'm climbing a mountain from left to right, if I have to go up to get to this point, this is the peak or local max, then I'd be climbing up to get to it, and then I would be descending in order to leave it. So, but look what this is really saying. What this is really saying is that f prime is greater than 0 to the left of the point, and f prime is less than 0 to the right of the point. So in other words, the sign of the derivative changes from positive to negative, and that's telling us that this is a max. So similarly, if I wanted to see if this point was a min, I'm going to draw the other type of critical number where there's a corner where it's a critical number because the derivative doesn't exist. Here, what we have is we have f prime is less than 0, so negative, and here we have f prime is greater than 0, so positive on the right. And you can see that this is a valley or a local min. So this is really what the first derivative test means, is that we can tell whether a critical number is giving us a local min or local max, or I should say, I'll get to the neither case in a minute, just by looking at the value of the derivative to the left and the right of that point. So this fact is what's called the first derivative test. And, by the way, just to review, why am I only concerned about critical points in the search for mins and maxes? Why don't I have to worry about any other points? There we go. Excellent. It's cool. I do this sometimes just to make sure that my audio is working. Yeah, because they indicate. Let's see. Okay, so Zach's answer is actually correct, because we know that mins and maxes only occur at critical points. Anyone call the name of the mathematician who told us that? Yes, me. That's true. I did tell you that. Fermat, that is the correct name. Pierre de Fermat tells us that mins and maxes occur only at critical numbers or critical points. Okay, so a sort of more complicated picture of this, that's probably more typical of the type of problem that we're going to be seeing, is a function that has both mins and maxes. So here we have that's critical point number 1. This is critical point number 2. And what you can see is that here, the derivative in red. So here we have clearly a positive derivative, a negative derivative, separate where the derivative changes sign, and then positive again. So what you can see is that, this is clearly local max, and this is clearly local min. So if we had just used the derivative, found where the derivative was either 0 or does not exist, to find the points C1 and C2, we could then test whether for whether those critical points are a local min or local max, basically by just picking arbitrary points to the left and right of C1 and C2. I'll label these D1, D2, D3, and D4. All we'd have to do is evaluate, let's say, f prime of D1 and f prime of D2, etc., all the way up through D4, and that would tell us whether we have a derivative positive or negative to the left and right. It's worth noting that you can pick, and this is an important technique, you can pick these points arbitrarily, and you pick them to be values that are really easy to evaluate, like you're looking for 0 or 1 or something like that. The reason you can just pick any point to the left of C1 and the right of C2, as long as you're not crossing over another critical number, is think about this. We know that the derivative, let's just focus on the interval from between C1 and C2. We know that the derivative cannot change sign, SIGN, in that interval, because if it did, if it went from positive to negative or negative to positive, it would have to at some point be 0. But if it were, then that would mean that there was another point, C3, where the derivative is 0. So I don't have to worry about the possibility that the derivative is going to be a different sign at some, in this interval, in the interval between C1 and C2, which means I can just pick any point in that interval. That's what lets me just arbitrarily pick D2 as the point that I want to look at. So we're going to see that in just a minute in the next example. The only rule is that you can pick D2 here if you're analyzing point C1. You can pick D2 there. You just can't pick it there. You can't pick D5 because that crosses over another critical number. And of course, at a critical number, the first derivative could change sign, SIGN. So let's see. Find and analyze the critical points of f of x equals x cubed minus 27x minus 20. So here's a function where we don't, not something where it's on the tip of everyone's tongue to know what it looks like. So without even drawing it, we can still figure out where its critical points are and whether they are mins and maxes. What this foreshadows is going to be the section we'll do two sections ahead, where we'll actually be able to sort of sketch at least the rough shape of a graph just from its derivatives, just by looking at things like where its mins and maxes are, whether it's increasing or decreasing on a particular interval. But for now, let's just say whether the points are mins and maxes. So f prime of x equals, take the derivative, that's going to be 3x squared minus 27. So we're going to find critical numbers. It's going to be f prime of x equals 0. So that gives us 3x squared minus 27 equals 0. 3x squared minus 9 equals 0. X squared minus 9 is only 0 when x equals plus or minus 3. So the critical numbers are 3 and negative 3. Okay. And of course, we can just say that f prime of x is defined everywhere. So there are no f prime of x dne type critical numbers. Usually, it'll be fairly clear whether you have to consider the possibility of non-existent, points where the function is not differentiable. But clearly in this case, since the function that we defined for the derivative, since it exists every place, we know the function is differentiable everywhere, and we're only looking for critical numbers where the derivative is 0. Okay, so now what we want to do is classify. We want to classify critical numbers based on whether their corresponding points are mins or maxes. So let's look at x equals 3. So what we want to do is choose point to the left and right of x equals 3. Now notice what we have here. We have, if I just write the x-axis, we've got 3 and negative 3 as the critical numbers. So what I'm going to do is let's just choose 4 as the test point. And fortunately, in the interval between the two critical numbers, we have the easiest point of all. We have 0. So I'm going to choose 4 and 0 as the points to the left and right of 3. So we have f prime of 0 equal to 3 times 0 squared minus 27 equals negative 27. f prime of 4 equals 3 times 4 squared minus 27. That's 3 times 16, which is 48 minus 27, which is positive 21. So what we see is that at this point, at f of 0, the derivative is negative, and at 4, the derivative is positive. So the slope changes from negative to positive across 3. So we conclude, so since f prime changes from minus to plus at x equals 3, x equals 3 is a local min. Okay. Yes. Sorry, Troy's asking, do we have to plug in a number for the left of negative 3, too? Yes, just not to check the point 3. We have to do that in order to check whether negative 3 is a min or a max. So now what we want to do is look at x equals negative 3. So fortunately, we already have a point to the right of negative 3. Now we just need to plug in, we need to pick a point to the left of negative 3. I'm just going to pick negative 4. So f prime of negative 4 equals 3 times negative 4 squared minus 27. Negative 4 squared is still 16, still positive 16. So that once again gives us 48 minus 27, or 21. So the derivative at negative 4 is positive. So f changes positive, f prime changes positive to negative at x equals negative 3. So x equals negative 3, the location of is the location of a local max. Okay, so the answer is f of 3 is a local min, and f of negative 3 is a local max. Okay. Any questions about that? Okay. Someone asked yesterday, it's probably worth, maybe somebody else has a similar question. It said, how can it be that the negative number is the max and the positive number is the min? So let me just try to draw roughly what this function would probably look like, sort of a standard cubic kind of function. So what we're seeing here is we've asserted that this is where the max is and this is where the min is, which looks like it's the wrong order. But remember, what these are giving us are the locations of where we think the y values are going to look like, mins and maxes. So what we're really talking about here is if this is a max and this is a min, we're probably looking at a function. Right. Right, for trying to do it that way. we're probably looking at a function that looks something like this. So here, f of -3 actually is greater than f of 3. So that's why the local max occurs here. Here we've got f prime. Clearly, if you look at the slope here, we have f prime is greater than 0, and f prime is less than 0, and f prime is greater than 0 again. So that's probably what the function that we're talking about looks like, something like this. Okay. Anyone have questions about that? Okay. The thing I want to point out is that the first derivative test may actually tell us that function is not either a min or a max. I'm just going to skip ahead a couple of examples. So we analyze and try to analyze the critical points and the increase and decrease behavior of f of x equals x cubed. So here what we can see is that f prime of x is equal to 3x squared. Okay. So if we try to figure out where is f increasing and decreasing, we can do is we solve 3x squared is greater than 0 and 3x squared is less than 0. So what we can see is that 3x squared is going to be greater than 0 for going to be either if x is greater than 0 or x is less than 0, because if I square any non-zero number, I'm going to get a positive number. And where is 3x squared less than 0? The answer is nowhere. So this is a function that's entirely increasing and it's not decreasing anywhere. So consider what it looks like if we graph this function. I'm just using this because most people know what x cubed looks like. So a cubic function, the basic cubic function, looks like this. So what we have is we can certainly see that f prime is going to be 0 only where x equals 0. So the only point where the derivative is 0 is at x equals 0 itself. But if you look at what's going on here, we have f prime is greater than 0, this point, at this part of the graph. And then here we also have f prime is greater than 0. So the derivative is not actually changing from positive to negative or negative to positive. It's just remaining positive. All it does is it kind of touches down on 0 and then goes right back up again. So it's possible to get a critical number that is neither min nor a max. It can just be a critical number that looks like that, where the function flattens out but never actually turns around into a peak or a valley. So it's not the case that you're always going to be able to find the number as a min or a max just because you found that it was critical and used the first derivative test. It might tell you that the critical number is neither of these. Okay. All right, so is there any questions about the first derivative test before I go on from here? Okay. So let's see. we go on to the subject of concavity. So we've seen that there are a couple of different things that we can say about the shape of a function. We've seen that, we know now that an increasing function looks like that. That's increasing. But that's not the only shape that we can talk about. We can also talk about shapes that look like this. Say this function, is this function either increasing or decreasing? And the answer is it's neither, but it does have this feature that it appears to be sort of smiling upwards, where it's like a bowl rather than a hat. And then we have kind of the opposite situation of this, where function is frowning downwards. Now, if you notice, if I actually follow the slope of the function, it's not really the case that it's either increasing or decreasing. It's actually doing both in that interval, but there does seem to be some sort of uniform property of the function, of either of these functions, which is this one is pointing up and this one, and the one on the right is pointing down. So what we say here is that this is concave up and this is concave down. Now, the reason I'm talking about these is because, of course, they do have formal definitions. It's not just a question of looking for the smile or frown. Oh, and by the way, of course, a function might actually switch from up to down. One of the functions that I did. Here, it looks like it's pointing down. Here, it looks like it's pointing up. So there must be some point in the middle where it actually changes from a smile to a frown. And we'll get to that in a minute. There's a name for that point. But let's just go on to the formal definition. So if you look at function and say function is differentiable in the open interval AB, we would say that f is concave up if f prime is increasing on AB and concave down if f prime is decreasing on AB. So let's take a look at what that means. Let me draw the concave up function again. So here's concave up, and just for future reference, I'll draw the concave down function. So let's look at what the slopes look like here. So I'll just put in some tangent lines. Little line segments indicating the tangents. If I had to just take a guess at what these slopes are, again, I'm just gonna eyeball it. Say this is roughly a slope of, it looks like it's downward and very steeply downward, so that's about -10. This is also a downward slope, but not nearly as steep, so let's call it m equals -1. That looks like horizontal, so it's m equals 0. Here's m equals 1, and here's m equals 10. So it looks like the slope, as we go from left to right, goes -10, -1, 0, 1, and 10, just at points, at arbitrary points that I pick along the x-axis. So, and then here we have sort of the opposite situation. We've got a positive slope of about m equals 10, m equals 1, like the m equals 0 slope. Here, m equals -1, and here we have very sharply downward, we have -10. So here we go 10 to 1 to 0 to -1 to -10. So what we can see is that the slope, and this is sort of the characteristic feature of a function that's concave up, is that its slope is actually increasing. And for a concave down function, the slope is increasing. I'm not talking about the absolute value, the steepness. I'm saying numerically, it is the case that we start here looking at the function on the right. We start here with a very strongly positive slope, and then it gets lower and lower and lower. It goes to 0, and then it becomes a very strongly negative slope. So what this means is that since this is equal to f prime in both cases, what that means is that f prime in the case of a concave up function is increasing. And in the case of a concave down function, f prime is decreasing. So what that means is that f prime of x, we know what a decreasing function looks like, is that the derivative of f prime must be greater than 0. And here, so the derivative of f prime, as you might expect, must be less than 0. We know that through the monotone function theorem, that we can tell whether a function is increasing or decreasing by looking at whether its derivative is positive or negative. So here what we're interested in is whether the derivative function, f prime itself, is increasing or decreasing. But we already know the other name for that is just f double prime of the second derivative. So a concave up function is one where its second derivative is greater than 0. And a concave down function is one where its second derivative is less than 0. And of course, as is often the case, that exclamation point is not for factorial, but rather for excitement. Oh, come on, can't I get a comment for that? Thank you. Okay. Just checking everyone's listening. Okay. So this brings us now to another way of classifying a critical point. Okay. Brings us to the second derivative test, which says that if C is a critical number of F, if C is a critical number of F, then if F double prime exists, then if F double prime of C is greater than 0, F of C is a local min. If F double prime of C is less than 0, then F of C is a local max. And if F double prime of C equals 0, then the second derivative test is inconclusive. So this is another way, in addition to the first derivative test, of determining whether a critical number gives us a min or a max. The only problem is it doesn't always work. Now, first of all, why does it work at all? The picture makes it kind of easy to see why it would work. So here's kind of a nice function again, y equals f of x. So here, if I just draw these in, now that we know what the function looks like, clearly this is a max and this is a min. But look at what's going on here. The max appears to be sitting on top of a concave down function, and the min appears to be sitting at the bottom of a concave up part of the function. So that's where you get these rules. It sort of looks like they're backwards, that if f double prime of C is positive, then you're getting a min, and if it's negative, then you're getting a max, but this is why. So okay, so let's see, where's my example of this? Oh, yeah, okay. So before I go on, before I do an example of the second derivative test, the thing you have to note here is that it looks as if this function is both concave up and concave down. So we can say about this region of the function is that f prime prime is less than 0. And in this region of the function, f prime prime is greater than 0. So shouldn't there be some point in the middle where f prime prime is equal to 0? And there in fact is. This is what's called an inflection point. So just like functions change from increasing to decreasing, they can also change from concave up to concave down, and we have a name for the point where they do that. So an inflection point is a point where a function changes from concave up to concave down. So I'll just put that definition up. So an inflection point is a point where the concavity changes from concave up to concave down. And then we have this theorem that lets us detect where that is. So what this says is that if I have a point that looks like this, let's see. So this is a point C where we can say that f double prime of C is equal to 0. And notice that if I pick 2 points, x1 and x2, what we're going to find is that f double prime of x1 is greater than 0 and f double prime of x2 is less than 0. So f changes concavity across x equals c, not x equals 0, x equals c. So c is an inflection point, not an inflection point, inflection point of f. Okay. So let's see. All right, so let's do an example of that. I actually want to do this one. So let's analyze the critical points of this function of f of x equals 2x minus x squared e to the x. Let's see. All right. So what we need to do is, first of all, find the critical points. In other words, what we want to do is find whether they're mins or maxes. So we need to, first of all, find the critical points. So we're gonna find the first derivative of x and set it to 0 and find where it's undefined. So this is going to be 2x minus x squared e to the x plus 2 minus 2x e to the x. So grouping everything together, that's going to be e to the x and 2x minus x squared plus 2 minus 2x equals 2 minus x squared e to the x. There we go. So what we want to do is, first of all, f prime doesn't have any D and E points. So we don't have to worry about those types of critical points here. We just have points where f prime might be 0. So let's solve f prime of x equals 0. That gives us 2 minus x squared e to the x equals 0, or x equals plus or minus square root of 2. So those are going to be the only points where those are going to be the only critical numbers. So the critical numbers are square root of 2 and negative square root of 2. All right. So we've now found the critical numbers. We just want to apply the second derivative test. So first of all, we need to actually find the second derivative. So f prime prime of x equal to, going to be, myself a little more space, f prime prime of x equals 2 minus x squared e to the x, because I'm just using the product rule here, plus negative 2x e to the x. So that's going to be e to the x 2 minus x squared 2 minus x squared minus 2x. Okay, so what we want to do is now substitute or plug in critical numbers into f double prime. So we have f prime prime of square root of 2 going to be e to the square root of 2, 2 minus square root of 2 squared is 2 minus 2 root 2. That's clearly going to be, so this is going to be 2 minus 2 is 0, and then minus a positive number. This is going to be negative. I don't really care what it is. I just care about the fact that it's negative. And f double prime of negative root 2 equal to e to the negative root 2, 2 minus 2, and then I have plus 2 root 2. That's going to be greater than 0. Once again, I don't care about its actual value. I just care whether it's positive or negative. So what that allows us to say is that f of square root of 2 here, we see that at this point, at root 2, draw it here, square root of 2, negative root 2. At square root of 2, we have concave down. So that means that f of root 2 is a local max. And here we see that at negative root 2, f is going to be concave up because its second derivative is positive. So f of negative root 2 is going to be, in other words, here we have as a function that looks something like that. And here we have one that looks something like that. So at a negative root 2, f is a local min. Okay. Ooh, I'm a minute over. I'm sorry. So, all right. So there's that should take us to roughly the end of 4.4. What I want to remind you is that as of now, actually, I think I said it to start, this week's quiz is open for the next 24 hours. It's on L'Hôpital's rule. You can find it on Canvas. We're going to resume quizzes on Monday. Monday's quiz will be on linear approximation, possibly another topic, but there will be linear approximation on it. And I will tell you the format of that. I know many of you have still had some questions about linear approximation. Sometime today, I'm going to make a video that you can watch that goes through a couple of the different types of problems. I think that's probably the most efficient way to do this. And so that's that. Anyone have any questions at this point? Someone's going to have to explain that one to me at some point. Where can we find the quiz? It is on Canvas. Go to quizzes on, go to assignments on Canvas, and it's under quizzes. It should also appear on your homepage, and I also emailed it to everyone yesterday. No, Zach, it's not that we're always doing 2 quizzes a week. It's just that I didn't have with the switch to the online teaching, I didn't have a quiz ready for Mondays. Uh, I didn't have a quiz ready for Tuesday's recitation, so I decided just to give it on a lecture day instead. But we're going to resume. Oh, I'm sorry, I said Monday. I meant Tuesday will be the quiz because your recitation is on Tuesday. Thanks. My other class has the recitation on Monday, so thank you. So it will normally be aligned to the recitation day. Yes. Although it'll be like a 24-hour window starting after your recitations, so you'll actually have a little time on Wednesday to do it, but it will be deployed on Tuesdays. The current quiz, Justin, the current quiz is on Canvas. There may be times that the quiz will be on Sapling, but today's quiz is on Canvas. I reserve the right to use either of them. In this particular case, I didn't find any good Sapling problems that could be turned into a quiz, so I wrote my own and put them on Canvas. But if there's a really good Sapling problem for a quiz, I might make it on Sapling. So I know it's a little bit disjointed. It just seemed like, keeping your options open seemed like the best thing. By the way, if anybody, as I do with my other class, I mean, I can stick around for a couple of minutes. If anybody wants to leave and there are a small enough number of people, you can stay and I can turn everyone's microphone on so we can talk if anyone has anything they want to ask. Question is today's quiz multiple choice or open ended? I'm going to let you see the format when you see it. So. Oh yeah, you couldn't find it yesterday because I just set it on a timer to start at 11:40 today when class was over. No, Eric, it's on Canvas. Ah, you too.